The learning component of the model includes crafting classroom activities according to the best principles of promoting learning. The principles of learning are active involvement, patterns and connections, informal learning, direct experience, reflection, compelling situation, frequent feedback, and enjoyable setting. More information on this can be found in the Technology as Facilitator of Quality Education model. The students in this 9th grade algebra class are studying quadratic equations. The teacher has the students review the general form and the vertex form. Then she gives the students a worksheet to help them discover the relationship between the factored form of an equation and its graph. The students use graphing calculators along with paper and pencil to solve the problems. The students display active involvement as they work cooperatively to complete the worksheet. They participate fully in the activity, and they display creative thinking when they relate the task to their prior learning. The students also engage in the construction of knowledge as they develop their own understanding of factoring.
And then general form you just factor it back out, so
Be y equals x cubed squared, sorry.
and then negative 3x is negative 7.
XX.
You do negative 3x plus the negative 4x, negative 7x.
So it'd be negative 7x.
Minus 7x.
Woo!
You just plus 12.
Like, this is going all over my head.
Okay,
Moment.
you guys got the
No, I don't got the factor.
We don't got the
form
factor
yet.
form. Remember, it's just the opposite of the two x-intercepts.
Is
It's
that
going to be x
20
minus 3 and the x minus 4.
Oh.
Remember we did that on the other side?
plus 12?
So they're both negative, right?
Yeah, because they're positive.
Right.
And
then
then you
what's
just factor it
general?
out, so then it'd be x squared.
X squared. Oh, I see.
Oh,
okay.
And then the whole thingy.
Oh my God.
The students receive frequent feedback while they complete the worksheet. The teacher provides corrective feedback as she circulates among the students. She points out specific errors and gives the students cues to help correct them.
I'm going to disagree with you in number 3. Number 3, you're telling me it's prime, aren't you? Okay, why do you know it's not prime?
Because it was negative. They were saying it was prime because it had negative x and it's so confusing.
Go back to the y equals. Why is that one not prime?
So negative x would have anything to do with, or would have barely anything to do with numbers.
Here's her graph. She typed that in again, number 3. Why is that not prime? What does it have
It
to?
goes through the x.
It passes through the x-axis. Okay. On the other side, you told me it was prime when it didn't go through the x-axis. This does. So you can't write prime on your paper. What are your intercepts?
The teacher helps the students see patterns and connections among the concepts they are learning. The students demonstrate flexible thinking as they connect their previous knowledge of graphing to a new learning context.
Okay. Did you discover anything up through problems number 1 through 5?
Yeah, it's the opposite.
Say it again, Andrew.
The x-intercepts are equal those are the opposites.
Okay. So I haven't asked anybody to do this yet, but you see you have the factored form listed on the board. What do you think that equation would look like? Y equals what?
The opposite of this number. The opposite of that number.
Think you could come up with a form then?
Equals x minus.
Let's call these roots. Remember we talked about x-intercepts being the same thing as roots? Let's call this having a negative 4 root and a positive 1 root.
Okay.
We can use the variable r then.
Well, 2 r's and
You can designate them as R1 and R2.
Okay, negative 1, 1.
Okay, do you guys see that? He wrote y equals x minus R1 and x minus R2. Ray, did you see that?
Yeah.
Okay. So what I think you guys just discovered there is the factored form of the equation. So now you can use that to answer your questions 6 and 7.
After the students have completed the worksheet, they establish patterns and connections by explaining to the teacher and the class what they discovered.
Okay, we started off class looking at the general form and then the vertex form, and you were supposed to come up with the factored form. Which group would like to share that with us right now? Taylor, go ahead.
A parentheses x minus r1.
What does R1 mean?
The root, the first root.
The first root?
And then in parentheses x minus r2.
Can you explain why it's minus?
Because it's the opposite of the roots.
It's the opposite of the roots. As I walked around, all of you were telling me that that's what you noticed. That was the pattern that you discovered, that all the x-intercepts, those values were opposite of the values you put in when you factored it. Okay, and that was important to discover.
The teacher asks the students to apply their new knowledge to a real-world problem. The students establish patterns and connections as they go through the process of solving the problem. They show flexible thinking by integrating their prior knowledge in a new context. They also engage in sense-making when they discover the real-world meaning of the new concepts they've learned.
We are going to apply what we just learned. We are going to answer this problem. And it says, suppose you have 24 meters of fencing material, and you want to use it to enclose a rectangular space for your garden. Naturally, you want to have the largest possible area for your plants. What dimensions should you use for the garden? Okay, so you are seeing some patterns here. As the width increases by 1, the length decreases by 1. Go ahead and draw the next 5 gardens for me then. You can fill in your table for the next 5. So let's fill in the area column. It would be 0, width times length.
11. 20. 27.
Okay, stop. Stop. Let's look at something. Increasing, increasing, increasing. Will it continue to increase?
Yes.
At a certain point,
All right, 8 and 4s, 32. Then we have 35. And then we have 36. Oh, and then we have 35 again. Then we have 32. Okay? Do you see this right here? Is what we call our maximum area. And the dimensions would be 6 by 6. Okay, now what we're going to do is we're going to take a look at what this looks like graphically. So let's change the window again. I want to go 0 to 15. Yeah, I only see 2 of them, didn't we? And what should our y's go from? To 30. Our largest value is 36. How about 38? That sounds good. Okay, and there's your data. What is the real-world interpretation right now of x being 0, scroll down there to the left, and y being, nope, I can't, that's the best I can get. Who can tell me what that means right there? What's the interpretation of that? That's where you'd have the smallest area. Okay, right there. So what does this tell me about the problem I asked you? It says that if I have 24 meters of fencing, I should build my fence to be a 6 by 6 because that adds up to 24, and it would give me the largest area. It would give me the maximum point of 36. Okay?
The teacher extends the students' understanding of factoring through an experiment. The students use motion detectors called calculator-based rangers to find out how high they can jump. The experiment requires students to jump in front of a motion sensor, which measures the distance to the wall behind the jumper. Although the data collected is linear, a parabola is used to model the time the jumper leaves the ground to the time the feet return to the ground. The students establish patterns and connections when they conduct the experiment. They engage in sense-making as they apply meaning to the algebraic concepts they have learned.
Now, here's what we're going to do to figure out your jump height, because this is measuring distance versus time. It's not measuring the height of your jump. There's a physics formula, and it comes from Newton's law of motion that is going to be on this handout that I give you. It's based on the force of gravity. It's an equation, and the equation is in the factored form. Okay? And what we're going to do is we're going to place a parabola, so to speak, on these peaks. Because the parabola, if I'm able to put a parabola here and here, what will the x-intercepts of that parabola tell me? The time. And the formula requires you to fill in the time. Fill it in for root 1 and for root 2. And then do all the math, and then the y value that's going to result is your jump height. So you're going to have to calculate your jump height by placing the values of the roots, which are the times, into the equation. Who has calculated some jump heights already? Okay, will someone in this group come over and explain to this group here how you're getting those values?
Do you have to solve it then? Technical equations and stuff. I'm not gonna go
Okay, what do you want?
They don't know what to do with those numbers.
I know.
I kind of do, but do we have to solve it then? Like,
Okay.
to make it equal to 0?
You put -192 in your y equals.
And then,
Okay.
-192.
Right.
In parentheses x, because you don't have a t variable.
oh, so I just
Minus your first time, which is time left. Then you put the 2 parentheses in the x minus the second time, which is your landing time. Then you get your parabola.
Oh, and then we find that. Okay, I get it.
Then you find what, Holly?
The maximum or whatever, right?
Why?
Because that tells you how high you jump.
The teacher provides more opportunities for frequent feedback by giving the students the chance to practice the skills they have just learned.
Here's how I'm going to assess how well you understand what we did. We have 2 people jumping up here, Al and Allison. And we've got some information that's listed there for you. I would like you to tell me something about these 2 people. Okay? You also need to tell me something about when they took off, when they returned, what's the difference between their plateaus at the top. Tell me a story about these 2 people.
This activity also gives the students a chance for reflection. They engage in a transfer of knowledge as they extend the skills they have learned to apply them in a new context.
Tell me what these 2 numbers being different mean.
She made a different circle.
She didn't land in the same spot. She landed closer to the CBR or further away? She landed closer. You can tell that by the graph too. Okay? Now, what was her jump height?
345 centimeters.
345. We're still doing inches. 345 inches. Okay, now, I put that up there for a reason. What must have Allison had to do in real life?
She stepped away.
Just step like this way.
She jumped.
She could have jumped out away from it and then jumped in. That would be good. One thing she could have done. What else could have she done?
Held, like jumped onto something.
She could have grabbed up onto the lights up there, hung up there.